Welcome back, everybody. In this unit, we're talking about erosion. So our goals for this lesson are for you to be able to first explain the process of weathering, erosion, and deposition, then to understand how streams develop over time, and finally to identify and delineate watersheds. So this lesson is really coming in the context of the interaction between internal and external processes on the Earth. So the shape of the Earth's surface, the place where we all live on the surface, is shaped by the balance between internal and external forces. Internal forces are things that are building up the landscape. So plate tectonics, for example, is a big internal force. It pushes things up. It creates mountains and volcanoes and so forth. And then we have external forces coming from outside that are tearing things down. And so in this lesson, we're going to be looking at one of the main external forces, which is erosion. So we have plate tectonics building things up, erosion tearing them down. Internal and external forces, and the balance between those will shape the way that the exterior of our Earth looks. And it's important to understand that erosion is really just one part of a series of processes. So erosion is the middle part of the sequence of events that goes from weathering to erosion to deposition. So we always want to be thinking in terms of weathering, erosion, deposition. Weathering, erosion, deposition, so that we can follow things through those three stages. So weathering is the breakup of solid material. So we've got various sorts of solid material making up our Earth, and weathering breaks that up. So instead of being stuck together in one big chunk, it now can be mobilized. Bits of it can be made to move. And we have three main types of weathering, three main ways that we can take a solid object like the gravestone that you see in the photo there and break that up. So mechanical weathering is weathering that's done by the application of physical force. So just a physical force pushing or rubbing or stretching on something that causes it to break apart. So that can be brought about by the motion of things like water and air and sediment. So if air is blowing across something a lot, that can loosen bits of it, or water flowing across something, or abrasion by sediments that are carried in the water or air. It can also be caused by expansion and contraction from heating and cooling. So as a solid object heats and cools, it's going to expand and contract just a little bit, not enough that you can usually see it with your naked eye, but it's happening. And it's the kind of thing that engineers have to account for when you build a bridge or a wall or something. You have to think about how much your materials are going to expand and contract in response to the temperature changes that it's going to be subjected to, and understand whether that's going to weaken your materials, whether you need to build in a way that's going to allow that expansion and contraction to happen without causing further damage. So just the cycle of heating and cooling that you get over the course of a day, over the course of a year, can cause mechanical breakup of pieces of things that had been solid. And then another important mechanical weathering process is what's called frost wedging. So this is something that'll happen any place where you regularly get temperatures dropping below 0 Celsius and water freezes, because most materials are at least a little tiny bit porous. So we might think of rocks as being, solid, they don't have any space in them, but most types of rock, a little bit of water can soak into tiny little pores in that rock. And if water gets in there and then freezes, water is kind of an unusual substance in that it actually expands when it freezes. And you've run into that if you've ever put a drink in the freezer to try to get it to cool down really fast and forgot about it, and you go back to it later and it has exploded all over your freezer. Because as the water in your drink froze, it expanded a little bit, and your can was already entirely full of whatever beverage you had there, so that expansion of the liquid as it froze into ice burst it apart. So the same thing is happening inside rocks. So little bits of water get soaked into them, and then they freeze, and that ice expands, and that exerts some force, pushing the walls of that little pore apart. And so that can eventually cause cracks and breaks to form in that rock. So that's something that we see a lot here in Pennsylvania, where we routinely get temperatures falling below freezing throughout the winter. So that's mechanical weathering, with application of physical force to break things apart. We also have chemical weathering. So chemical weathering occurs when we get chemical reactions that weaken or break up materials. So one of the really important sources of chemical weathering is acidity in water that either flows across or falls as precipitation onto things. So if that water in its pure state is neutral in pH, it's neither an acid nor a base, but there's lots of things that can make that water a little bit acidic. And so those acids can react with the chemicals that make up your rock, and those chemical reactions create new materials and break apart the rock that you have there. And that is, of course, enhanced if you have pollution that makes your water even more acidic. So we had for many decades a serious problem in the eastern United States with acid rain, because we had a lot of industry that was producing a lot of pollution that was putting substances into the air that would then get absorbed into precipitation when it fell, and those substances were acidic. And so the acid would eat away at rocks, it would eat away at buildings, and you can still see that if you look at older buildings. You can often see them having been damaged on the outside by that acid rain. Now, luckily, that's a pollution issue that we have, to a significant degree, gotten under control. So the acid rain that we have today is nothing compared to what it was back in, say, the 80s. But there's still that risk that pollution can make our rainfall more acidic, and that then those acids are going to have chemical reactions with materials that they fall on and cause chemical weathering. Then the third type of weathering is biological weathering. So the actions of living organisms can break things apart. So you have things like the roots of plants. So the roots of plants get into tiny cracks and pores in, say, a piece of rock, and then as that root grows, it's going to expand a little bit, and it's going to break things apart. We have the actions of burrowing animals. They dig through stuff, and that can weaken and disrupt things that had been solid and packed together. And then we have human and animal traffic. So whenever you walk somewhere, just the force of your feet walking on stuff has a weathering effect. And so if you are walking across something, you are slightly breaking it down with every step that you take. And you can see this really easily when you look at places where people have walked across soil, because that's easier to break down. You can see the tracks left by people as they go, and the way that their foot traffic has broken up the soil. But if you get enough foot traffic against something that is solid rock or concrete or something like that, you're going to get a breakdown as well. Cars. The traffic of cars breaks down the materials that the cars are driving over. That's why we have to keep fixing, or one of the reasons we have to keep fixing the roads all the time. All the other forms of weathering are also affecting our roads. Animal traffic as well. So, and that's especially notable for livestock. So people get large numbers of animals together and, have them walk along particular trails, say driving cattle to a place that they're going to get sold and slaughtered, for example. And you get a lot of foot traffic from those animals, and that can break up that soil. It's actually been a major issue in Australia, because until European settlers arrived, there were no hoofed animals living in Australia. So all throughout Australia, you had kangaroos that have soft pads on their feet, kind of like a rabbit. So they were jumping on the ground, and that had a different effect on the soil than the hooves of sheep and cattle that were brought by European settlers. And so you've had a lot of increased weathering of the soils throughout Australia, wherever there are large areas that have become sheep and cattle pasture, because it's a different kind of foot traffic from the livestock there. So weathering is things that break up solid materials, solid packed together soil, solid rocks, as they get broken into bits that can be dislodged. We've got weathering. Once weathering has occurred, then we can get erosion. So erosion is the transportation of weathered material away from its place of origin. So something breaks up, and then bits of it get moved somewhere else. And the moving stuff away is erosion. And erosion can be driven by water or air or just by gravity. So air can come through, winds can blow weathered material away and move it to a different place. Water can flow across a landscape and pick up sediments that have been eroded out of the base material, move them somewhere else. And when things are loosened up, they like to move downhill. So a pretty basic process that affects everything on our Earth is gravity. Everything wants to go downhill if it can. And so that's going to be continuously happening anywhere there's a slope. Everything on that slope is going to be wanting to move downhill. And it could move downhill quickly or slowly. So when the material on a hillside is moving downhill slowly, we call that creep. So if you have a hillside that has soil or loose rocks on it, those are sliding slowly downhill, and you're getting that creep. And one of the ways that you can tell that that's happening is by looking at anything that was placed in the ground vertically when it was first installed. Over time, any vertical object on a hillside is going to start to lean downhill because all of the soil that it's put into is starting to slide downhill, and so it's going to lean that object over as it goes. I should do it the other way to match what's on the screen there, but you can see that fence there, right? It's fence on this hill. That fence was installed with vertical fence posts, right? That's how you build a fence. You put the fence posts in vertically. That is clearly an old fence, though, and so you can see how much those fence posts are leaning over time because of the creep of that soil down the hillside. And it's an interesting thing to keep a lookout for as you go around various places, is anytime you see something that is old and that was presumably installed vertically when it was first built, you can often see that it's leaning over slightly if it's on a hillside. There are a number of examples of that around our campus. So if you take a walk around campus, keep an eye out for older objects, old phone posts, old fence posts, and you'll be able to see some of them starting to lean downhill due to creep. So creep is when it's happening slowly. We call it mass wasting when it's sudden. So sometimes a hillside will very quickly move downhill. So something that was just barely holding it up changes just a little bit, and that could be triggered by a variety of things. It could be triggered by an earthquake that shakes things and disrupts the balance of things that was keeping things from falling down the hill. It could be heavy precipitation because the water soaks in and basically lubricates the whole system. And so now stuff isn't holding on as well, and so it starts to slide downhill very quickly. It could be just over time, as things are creeping, they eventually got out of balance, and now a bunch of stuff falls down the hill. So we get something like a landslide or an avalanche. The larger category that those fall into is mass wasting. So that's sudden downhill movement of material. So that's a form of erosion. Another form of erosion to keep an eye out for is gullying. So when you have water flowing across a landscape, it's going to cause erosion. It's going to pick up weathered material and wash it away. And it's going to do that a lot if it's got a lot of energy behind it. And it's going to do it a lot if there isn't something holding that material down. And so in a case like that, where you've got a lot of water, not anything holding the the weathered material down, you get some sharp valleys carved out by that water. And that can happen even on a hillside where there's not a continuous stream, but where there's just water flowing down it whenever it rains. That water can form these sharp, narrow gullies that move a lot of material downhill very quickly. So a high rate of erosion happening there. Okay, so we have weathering, we break stuff up. We have erosion, we move it away from its point of origin, but it's got to go somewhere in the end. And when it goes somewhere, we call that deposition. So when that weathered material that's been transported by erosion eventually gets left somewhere else, then that is deposition. So erosion and deposition always go together. Whatever gets eroded from one place has to be deposited somewhere else. Whatever's being deposited in one place has to have been eroded from somewhere else. There's always a connection. They always come in a pair. Erosion from one place, deposition in another place. And so we can take environments and divide them into erosional and depositional areas. So we have areas where we're primarily seeing erosion happening, where mostly material is being removed, and we have depositional environments where mostly material is being left behind and being placed down there. And so the photo there gives you an example of a classic depositional environment. This is the delta of the Mississippi River. So the Mississippi River, as it is flowing, it is eroding a lot of material. There's a lot of sediment being carried in the water of Mississippi and of all of its tributaries. And so those are being picked up in erosional environments upstream. But then as the river reaches its mouth, it begins to deposit that sediment. So it begins to leave stuff behind. And so it builds up all of this land in the delta as this eroded material is left there as the river flows into the Gulf of Mexico. And so this deposition is essential to human life. All of our fertile farmland occurs in depositional environments because we need to deposit new soil to maintain the soil that we're growing our crops in. So we need deposition to be happening, which means we also need erosion to be happening because deposition can't happen without erosion. But too much deposition in the wrong places can be a hazard. So if we get too much deposition or deposition happening in the wrong places, we can bury infrastructure, houses, roads, etc. It can block navigation. So it's a very common thing that the mouths of rivers have to get dredged out. So we have to basically send a boat in with a big scoop to dig deposited material out of the riverbed to keep it wide enough and deep enough for boats to come through. So this is one of those cases where our society would really like things to stay stable. We'd like to build a port and know that the same boats can come in and out, that the size of the channel isn't going to change, but the size of that channel is always changing. We're either getting erosion or deposition going on everywhere all the time. So our landscape is always evolving and always changing. And we sometimes try to halt that process, try to offset that by removing deposited material or replacing eroded material. But we are kind of fighting an uphill battle there because this process of erosion and deposition is just happening all the time. So let's look at a stream and see what's happening at different parts of that stream, because streams are one of our major agents of erosion, one of the major things that transports material from one place to another, much more so than, say, wind, and on a larger scale than gravity alone could do. So the basic starting point for understanding how streams work is to remember that water flows downhill. And that may not seem like a very stunning piece of information that you've just learned, but it's the foundational thing that you always have to remember, and that remembering the water flows downhill will help you sort out what's going on in a lot of contexts. If you get confused about stuff, just say, okay, well, so the water's flowing downhill. What does that entail? What does that imply or lead to if we remember that water's always flowing downhill? And it's flowing downhill over land, so just across the ground. It's flowing in stream channels. So when you get enough surface water together in one spot, it's going to form a semi-permanent or permanent stream. And it's also flowing underground. So we have the movement of water underground that's still going downhill. It's still flowing downward. It's just doing it beneath the surface. These streams that we have are being fed by a combination of precipitation. So we have water falling from the sky, right? One of our key flows in our water cycle, and that precipitation flows into streams. We also have snow and ice melt that feed streams. So we get frozen precipitation that falls at high altitudes, and at certain times during the year it gets warmer, some of that starts to melt, and the melting of that frozen precipitation from snow, from glaciers, etc., feeds into our streams. And then some of that groundwater will flow out into the stream. So if the stream cuts down below the level where the groundwater is, that groundwater will find itself flowing out of the ground into the stream. So groundwater feeds into, but then also can be taken out of our streams. It's a constant back and forth of water between the surface stream and the groundwater. And as streams are going downhill, they frequently join together. And so when two streams join together, we call them tributaries. And we often talk, if it's clear that one stream is much bigger and more important, we'll often say, well, you know, there's the main stream and then the tributary enters it. But really everything is tributaries coming together into larger streams as we go downhill. So the structure of a stream is going to be this branching structure, where if you were going upstream, you would see it keep splitting apart into smaller tributary streams. If you're going downstream, those tributaries are joined together. It's very rare for a stream to split apart. If that happens, we call them distributaries. So tributaries come together, distributaries go apart. It's very rare for a stream to split apart in any big way. So, you know, it might split apart to go around an island, and you get distributaries in delta areas where you've got a ton of sediment being deposited and the river kind of breaks up into little channels. But you generally don't see a big river going across the landscape and just splitting in two as it goes. Generally, if that were to happen, one of those sides would eventually erode down and become the main stream and drop down lower than the other one, and now everything going downhill is going to go into the lower branch of that stream. So you see streams joined together all the time, and very, very rarely do you see them split apart as they go. And so that can be one way to look at a stream and tell what's going on, tell what direction water is flowing, what direction is up and what is down, is by looking at streams. Are they coming together or splitting apart? If you see two smaller streams come together and become a larger stream, you know you're seeing two tributaries forming the larger downstream channel. So because of the way streams join together as they go, we can define a watershed. So a watershed is the area of land that drains to a particular outflow point. So usually when the outflow point we're interested in is the spot where that stream either flows into a water body like an ocean or lake, or it's a point where two tributaries come together. And so we're interested in the watershed of one of those tributaries upstream of where it enters another larger stream. So that's usually what we're looking at. We have sort of the end of the stream is the point that we're interested in. And so then the watershed is all the land where precipitation that fell on that land would drain eventually down to that outflow point. So in this little diagram that you see on your screen, if our outflow point is at the bottom of the diagram where that to the bay arrow is, then everything between those red dotted lines is going to drain into that stream and eventually down to that outflow point. So any precipitation that falls anywhere between those two red dotted lines, if you imagine that precipitation, it's going to go downhill. It's going to find the shortest route downhill that it can find. It's going to end up in one of those little tributaries, which flows into the main stream there, and the main stream will take it down the diagram to that outflow point. So if you're ever trying to figure out what watershed am I in, you've got a point that you're considering, and you'll be doing this in your activity. You'll have some points to consider. Just think, if a drop of water fell at this point and it kept going downhill, and whatever was the quickest way for it to go downhill from this point, what stream would it end up in? So if you look at those red dotted lines on the diagram, what you can see is they're running at the peak of those ridges that run to either side of our stream. Right? The stream is going to be at your low point in the landscape because water flows downhill. So the divides between watersheds are going to run along the high points. They're going to run along those ridges. And so if you had a drop of water falling just to the right of the one, if you look where the mountain ridge label is there, if you have a drop of water falling just to your right of that line, it's going to go downhill and down into our stream that's featured on this diagram. But you can see if a drop of water were to fall just to your left of that line, it's flowing down the other side of that mountain. And so we can't see where it goes because the diagram is kind of cut off there. But presumably there's another stream over to the other side of that mountain. So that line, that's the dividing line. Water on one side of it flows to one stream, other side flows to another stream. So that is a drainage divide. Drainage divide is the high point that separates two watersheds. Another important thing to keep in mind is that watersheds are nested. So smaller watersheds make up a larger one. So the red lines on the diagram are defining the watershed for that large stream that all flows out at the bottom of the diagram. But you can see any of those little tributaries each have their own little watershed. So we've got the sort of sideways ridges on those mountains that divide water that flows into one tributary versus another. So each of those tributaries have their own mini watershed within the larger watershed of that whole large stream. So those sub-watersheds make up part of the larger stream's watershed. So that was just sort of a stylized diagram. Let's look at the watershed that you are living in if you are at Slippery Rock. And unfortunately that star got a little moved at some point in me making this PowerPoint, so it should be a little farther south, just to the north of Slippery Rock Creek. I apologize for that. I don't know how that moved there. I'll fix that on the PowerPoint that I put on D2L. So the town of Slippery Rock and the university lie between Wolf Creek and the upper part of Slippery Rock Creek. So Wolf Creek isn't shown on this map here, but you will have seen it when you were looking at the topographic map of Slippery Rock. We've got Wolf Creek flowing kind of to the west of the town of Slippery Rock. We've got Slippery Rock Creek flowing to the south. So the town is kind of in between those two creeks. So the town is going to be in either of those watersheds. Depending on where you are within the town, within our campus, you may be in the Wolf Creek watershed or the upper Slippery Rock Creek watershed. But those two streams eventually flow together to form the lower part of Slippery Rock Creek. So regardless of what side of town you're on, you're part of the larger overall Slippery Rock Creek watershed. Whether you are part of the sub-watershed for the upper part of Slippery Rock Creek, the sub-watershed for Wolf Creek, you're part of the Slippery Rock Creek watershed as a whole. Slippery Rock Creek flows down into Connoquenessing Creek, which then goes into the Beaver River. And so the map there is showing you the watershed of the Beaver River. So that encompasses things like Connoquenessing and Slippery Rock as tributaries of the Beaver. So water falling in this whole area of central western Pennsylvania, central eastern Ohio, flows eventually into the Beaver River and to the end of the Beaver River, where it enters the Ohio, near the towns of Beaver and Rochester. So any water that falls within the yellow area on that map eventually makes its way down to the mouth of the Beaver River, and from there into the Ohio River, which flows eventually into the Mississippi River near Cairo, Illinois, And then the Mississippi River flows out into the Gulf of Mexico near New Orleans. So if you were to pour some water on the ground outside one of our buildings at SRU, that water would eventually make its way down to New Orleans. So it would flow into one tributary, into another, and eventually out through the mouth of the Mississippi River. And so some of the streams in this sequence are called creeks, some are called rivers. There's no technical definition for the difference between them. The Connoquenessing, we could have called it the Connoquenessing River if we wanted to. It's just, generally we call smaller things creeks, larger things rivers, but there's no like official dividing line of what makes something truly a river or truly a creek. So, the names are kind of arbitrary there. But we can see we're getting to bigger and bigger streams as we go. So we have small streams that flow into larger, etc. So let's take a look at a topographic map and see how we can identify watersheds on it. So I want to take a look at two little streams that flow into the Allegheny River near the city of Warren, Pennsylvania. So this map, it's kind of zoomed in, so some of the labels are cut off. But you can see North Warren there, and then that main gray area that you see in the lower right of the map is the city of Warren. And so the Allegheny River is going across the bottom of your screen there, flowing in this section of it is flowing from east to west. So it's flowing leftward across the map that you see here. And you'll see two little tributaries that flow into the Allegheny on its north bank, which are Morse Run and Scott Run. So those are the two that we're going to look at to illustrate how we can identify watersheds. So Morse Run and Scott Run are both located in valleys, of course, right? Water flows downhill, so our streams are going to be at the bottoms of valleys, and we can see some of the characteristic aspects of a topographic map with those streams. So we said that contour lines will tend to create a V shape pointing upstream as they cross a stream. And we can see that in both cases, right? You see V-shaped formations of those contour lines, the brown lines, as they cross those streams, and they're pointing upstream. The V's are pointing away from the Allegheny because these streams are flowing into the Allegheny. So those V shapes that form as the contour lines cross those little streams are going to point away from the Allegheny. So in between Morse Run and Scott Run, there's going to be an area of higher ground. We're going to get a ridge in between them where the drainage divide is going to be located. And we can actually see in this case that there is a road. So the gray lines on this map are the smaller roads. The red lines are major highways. We've got a road that goes from Jackson Crossing up to Dunham Corners that more or less follows the top of that ridge between Morse Run and Scott Run. And so if you look at where I've got those two arrows there, if you imagine rain falling on the top of that ridge, the rain that falls on the western side of the ridge, it's going to try to go downhill, so it's going to go westward, and it's going to flow down into Morse Run. So the western side of that ridge, basically everything to the west of that road, is flowing into Morse Run. It's part of the Morse Run watershed. Any water that falls on the west side of that ridge is going to flow down into Scott Run. So anything to the west of that road is flowing westward downhill into Scott Run. So that road is more or less following the drainage divide because it's following the high point of that ridge. So anywhere along that road, if you just imagine some water falling and think about where's it going to go, what's the fastest way for it to go downhill, you'll see if it's to the east of Morse Run, it's flowing, or sorry, it's east of the road, it's flowing into Morse Run. If it's west of the road, it's flowing into Scott Run. So we can use this idea to delineate the entire watershed for each of these streams. So here I've drawn out the watershed for Scott Run. So that reddish blob there covers all of the areas where if water fell there, it would flow down into Scott Run and eventually out to the mouth of Scott Run where it flows into the Allegheny. Okay, so that's our drainage point that we're defining watershed for is the mouth of Scott Run. And so you can see anything within that red area, if it's going downhill, it flows into Scott Run. So it's following that road along the ridgetop between Scott and Morse. Is following, there's another road along another ridgetop between Scott and Irvine. Then it kind of cuts in closer towards that mouth as we get down to the southern edge of that, because you'll see there's a couple little valleys that don't have permanent streams in them that lie just to either side of the red area. And you'll see that those valleys look like if water fell into them, it would flow down through the valley and into the Allegheny without ever getting into Scott Run. So those are outside of the Scott Run watershed because water flowing there would go directly into the Allegheny. It wouldn't get into Scott Run. So we can delineate that whole watershed for that stream. And then we can also delineate the watershed for Morse Run. So here, this one's a little bigger. We had to go around several small tributaries, right? Morse Run's got one little unnamed tributary to the east and one little one to the west on this map. And so those tributaries are part of the watershed for Morse Run. So again, our outflow point at the Allegheny, where the Morse Run enters the Allegheny, and we can see that water is flowing into Morse Run. The two watersheds should meet up exactly. Just as I was trying to draw this in PowerPoint, it's a little hard to make it exact. So they should meet exactly in the middle there. But then you can see that the northern edge of that watershed is following the ridgeline along Yankee Bush Hill. So any precipitation landing on the southern side of Yankee Bush Hill, its best way to go downhill is to go down into Morse Run. So it's part of the Morse Run watershed. But anything landing on the north side of Yankee Bush Hill, its easiest way to go downhill is to go northward into Jackson Run. So that's not going to be part of the Morse Run watershed because Jackson Run isn't a tributary of Morse Run or vice versa. Right? They flow differently into different areas, even though they eventually come together, but they don't flow directly into each other. So they're not part of each other's immediate watershed. So we can follow that ridgeline all the way around and delineate that watershed for Morse Run. So we're just following those ridgelines and just keep thinking about if water fell here, what would be the fastest way for it to go downhill? If it goes into your stream that you're concerned about the watershed for, it's part of that stream's watershed. Okay, so let's talk about the formation of those valleys that our streams are flowing in. So the streams are flowing at the lowest point of these valleys, but they're also shaping the valleys. The streams are not just existing in valleys, they are carving those valleys out as they go because rivers are agents of erosion and deposition. So the steeper the stream is, the more energy its water has. So we've got a lot of positional potential energy when precipitation falls on an elevated area because it's high up. And so that's going to turn into kinetic energy as it flows downhill. And if it's flowing down a very steep hill, it's releasing a lot of kinetic energy as it goes. So we have a lot of energy in a stream that's on a very steep slope, and you have a lot less energy as it flows on a flatter slope. So the steeper the stream, the more energy. More energy means more erosion. So energy enables that water to pick up material, pick up weathered material, and carry it along. So high energy streams will have a lot of material suspended in them, a lot of sediment, and will be picking up a lot of stuff as they go. So they are going to be carving their valley downward very sharply. So a high energy stream is going to have a deep V-shaped valley, and that's what you see with A on the diagram there. And so the stream, when it's up in the mountains, it's coming down a very steep slope. It's got a lot of energy, and so it's cutting downward very quickly. And so it's going to create this steep V-shaped valley. As the stream gets out onto the plains there, it's now not on such a steep slope, so there's not as much energy, and so it's going to have a broad, wide valley. It's not carving itself downward into the landscape really quickly. It doesn't have that same kind of energy. And as that stream's energy decreases, it will begin to deposit material that it had been carrying. It doesn't have the energy to continue moving stuff along, and so it's going to start to drop it off. So we're going to see a transition from an erosional environment where we have high energy, steep streams to a depositional environment where you have low energy, less steep streams. And we can see those processes at work when we get meanders in rivers. So as rivers flow, they're not flowing in a perfectly straight line. They're going to bend and wiggle as they go. And each of these little bends or wiggles in a stream we call a meander. So you've got a series of meanders here in this diagram. And as a stream starts to meander, it's going to start to erode in some areas and deposit in others. So as the water comes around a meander, comes around a bend in the stream, it's basically slamming into the outer edge, the outer bank of that meander. And so it is exerting its energy at that outer bank. And so you're going to see heightened erosion on the outer bank of a meander. Meanwhile, you've got a lot less energy on the inner bank of that meander. And so sediment is going to start getting deposited on the inner part. We call that the point bar. So we have erosion on the outer bank of the meander, and we get deposition forming a point bar in the inner side of that meander. And what that's going to do over time is it's going to make the meander bigger, right? It's cutting into the outside of the loop and depositing stuff on the inside, so that meander is going to get bigger and bigger. It's going to get loopier and loopier. So over time, rivers become more and more meandering. Meanders get bigger and bigger. However, eventually those meanders may get cut off because that water, it's got a lot of energy and it would rather go straight. It would rather not hook around this big meander. And so if that water gets enough energy behind it, it can cut across the point bar and basically straighten the river back out. So this often happens at a time of flood. So when you have a flood, you've got a lot more water and a lot more energy, and that can enable a river to cut across the point bar and straighten itself back out. And so it's going to leave that meander kind of stranded. And we call that an oxbow lake. So it's curved like the yoke that you'd put on an ox, so it got called an oxbow lake. So what you see there in the left-hand side of your diagram, you got your oxbow lake, and you've got that meander. That meander used to go all the way out around where that oxbow lake is, but it cut across the neck of the point bar at some point and made the river a little straighter, a little shorter. So in places where you have a lot of meanders forming, you get meanders that grow and grow, but then eventually get cut off into oxbow lakes. The river straightens out a bit, but then starts to form new meanders. So you've always got this process where you've got erosion on the outer side of a meander, and you've got the deposition forming a point bar on the inside. And so what that'll look like on the landscape is a very steep bank on the outside where that erosion is happening, and a very flat, low point bar. So the erosion is cutting into that bank, cutting a kind of a cliff into it, and the deposition is forming a very low elevation, very flat point bar on the inside. So this is kind of a stylized diagram. Let's look at an actual place not too far from us at Slippery Rock. So this is the Connoquenessing Creek just south of the town of Connoquenessing. So you can see the stream running through the middle of this map here, and it's flowing generally from east to west here. And you can see it's making several big meanders. There's several big twists and turns of the creek as it's going. And if you look at the two meanders that are kind of looping northward, so there's one right there by the TJ's Hideaway label, and then another one south of the Clifford's label. I just screenshotted this off of Google, so it's trying to uh, show me some restaurants to go to. That's what those are. But you can see there's those two meanders that kind of loop up northward. And you can see from the shading on this topo map, the shading helps you kind of see the shape of the landscape a little more, that you've got a steep cliff on the outside of that meander. So you've got kind of a steep area just to the north of those two meanders. And that makes sense because they are eroding outward in that direction. Those two meanders are eroding themselves northward. And so you've got this steep cliff that's being eroded. Then on the inside of both of those meanders, you see it's very flat. So that's the point bar where material has been deposited by the creek, but the creek can't build it up very high above the water level that the creek might ever get to. So you've got very low relief at the point bar where the deposition is happening, steep cliffs where the erosion is happening. And then if you look in between those, you'll see a spot where we have a few oxbow lakes. So in between those two north-facing meanders, you can see that the stream kind of cuts across straight. But if you look just to the south of that, there's one of those cliffs very similar to what you see on the outside of those other two meanders. And so what we see happening there is that there used to be a south-pointing meander right there, and it was eroding into that hillside, creating that cliff area, and then the area inside was getting deposition. We were forming a point bar, but at some point, the stream cut across the neck of that point bar and straightened itself out. So now most of that point bar is left on the opposite bank, and you've got some oxbow lakes that are left behind in areas that used to be the channel of that stream, but it has straightened itself out at the present moment. So we can see in this little bit of our landscape, not too far from Slippery Rock, this process of meanders forming and the way that erosion and deposition are happening at different points to create the kind of landscape that we have there. Here's another interesting example of the interaction of meanders and the way that they change with people. So people often like to put borders along rivers and streams. It's a very convenient way to mark the edge of something. It's something that we're not crossing a ton anyway, so it makes a convenient border. So all around the world, there are lots of borders of countries, of states and provinces, of towns, counties, whatever, that are located along streams of various sorts. The catch is our human societies like to keep things fixed in one way. We don't like things to change, whereas nature is constantly changing. And so those streams are going to change. The meanders are going to grow and eventually get cut off, leaving behind oxbows, and then new meanders will form over time. So what do we do about the border? Do we change the border to match the new stream? Well, sometimes we do, other times we don't. So what you're seeing here is part of the Mississippi River, and you've got Arkansas on the west side and Tennessee on the east side, and they defined their border when those states were formed as following the channel of Mississippi River. And so you can see that border, the little black dotted line there, is very squiggly as it goes across. That's where the main channel of the river was when those states were created and their borders were defined. And that border has remained the same, even though the river has changed over time. So you can see some places where the border now follows an oxbow lake that was left behind by a change in the mainstream of the river. So the river has changed, the border has been frozen, and so now you get these weird little bits of one state on the wrong side of the river because the river's channel has changed. Okay, so I want to finish by talking about some of the ways that we might manage erosion. What do we do about erosion if we don't want it to be happening, if we're concerned about erosion causing changes that we don't want to see? Well, there's a number of things that we might do. So one thing we might do is having plant cover. So when we have plants growing on the ground, the plants shelter the ground from the impact of precipitation, which can be a form of mechanical weathering. When rain hits the ground, it exerts some force on it. And more importantly, plants have roots that hold soil together. So if you've got soil that's got a lot of plants in it, the roots are going to knit that together and reduce the amount of erosion. So making sure that we have plant cover growing places is a good way to stabilize soil and reduce erosion. We can also do things to harden our locations that we don't want eroded. So that can involve things like concrete walls or riprap. So riprap is what you see in the picture there. Whenever you see a stream or a hillside that's got these big chunks of rock on it like that, that's riprap. That's been put there to try to control erosion, because those big chunks of rock are a lot harder to erode than the soil that's underneath them. So they are providing a kind of protection to the soil and to that slope. It's going to be harder to erode with all those big chunks of rock on it. So we can do various things to harden and stabilize our surfaces and our hillsides to prevent them from eroding. We can try to divert water away from places where it's been causing a lot of erosion. So we can redirect our stream channels. We can install, pipes and culverts, or create little dams and things that are going to shift water to different places so that it's not flowing across the same spot, eroding it. We can also do things to prevent human activity from encouraging erosion. So if, for example, you're a farmer and you have a field and your field is on a slope, you would generally plow along the contour lines rather than up and down the slope. Because if you plow up and down the slope, you're making it easier for your soil to erode and be carried down the lines, the furrows that you make by plowing. But if you plow along the contour lines, so you're plowing at constant elevation, so it's going across the slope, that will inhibit erosion. So your furrows will kind of catch stuff as it tries to flow down the hill rather than encouraging it, giving it a little channel or pathway. The same thing happens with roads and paths. So if you are building a path that goes up a hill, you'll often make it switchback. It'll zigzag as it goes, so that you're walking closer to contour lines rather than cutting across straight up or down. And so that's nice on one hand because it makes it easier to walk. So you're walking farther, but you're not having to go up such a slope all the time. But it also inhibits erosion. A path that goes straight up a hillside is going to create a spot where erosion is going to happen more easily, and that path will quickly turn into a gully. Whereas if your path zigzags back and forth up the slope, then your path is cutting across the direction that erosion wants to go, and it's going to slow that erosion down. And that's a reason it's very important to stay on paths. If you are out for a walk or a hike in the woods and you're going up a hill and your path is zigzagging a lot, you may be very tempted to cut corners, right? To cut across. Sometimes it's like, the next bit of the path is just a couple feet that way, but I don't want to have to go all the way down around the corner to get to it. I'll just cut across here. But when you cut across there, you are encouraging erosion on a up and down kind of path. And maybe just one person isn't going to make that much difference. But if everybody did that, then they would tramp out a new path that would encourage erosion rather than inhibiting it. So it's important if you're out hiking, if the path is very zigzag up a hill, just stay on it, even if it means you're doing a lot of walking back and forth around the corners, because that's done that way to reduce unwanted erosion. And then finally, in kind of the most extreme scenario, we can replenish soil. So if stuff gets eroded away and we didn't want it eroded away, we can truck in more stuff. And so this is a thing that happens a lot along beaches. So beaches can be erosional or depositional. We have some beaches where a lot of new sand is constantly being deposited. We have other beaches where the ocean is taking sand away. And some of those beaches where the ocean is taking sand away are beaches that we want for, tourism, for recreation, etc. And so we'll truck in lots of soil and add it to the beach to replenish what got eroded. So that's sort of the extreme solution is if stuff is getting eroded, we don't want it to erode and we can't stop it from eroding, we can just put new stuff on. But of course, that gets very expensive and time consuming and can only be done on kind of a localized scale. So with that, I will wrap up this lesson and talk to you next week.